Hello, IB Physics. This is Ms. Getz here, and today we're going to look over some example reactions in particle physics. And so I have three reactions that we're going to do together right now. You can write these down on paper as you go, or you can listen right along to me. You can write them in your Notability file, whatever works for you. So I'm going to go ahead and get started with this first reaction where we have a proton and a pion minus that are turning into, so they're transmutating into a neutron and a pion zero. We want to figure out, is this reaction actually possible within the laws of physics? And so first off, I'm going to go through the families that each of these particles are. A proton is a baryon. A pion, proton is a baryon. It's made of three quarks. It's made of an up quark, another up quark, and a down quark. A pion is made of two quarks, and this is the pion minus, which is the opposite of the pion positive. It's like the antiparticle to the pion positive. So a pion negative has an anti-up quark and a down quark, which is just the opposite of a pion positive. And because it has two quarks, it's a meson. Then neutron is a baryon, because again, it has three quarks. It has an up quark and two down quarks. Down. And then the pion neutral, I had to look this one up because I didn't actually remember, is an up and an anti-up. So again, it's a meson because it has just two quarks instead of three, and it's a quark and an anti-quark. I'm going to use my IB packet to help me complete the rest of the conservation laws and figure out if this reaction is in fact actually possible. So to go through, I first need to figure out the charge of a proton, and I can do that by adding together two ups, which is 2/3 plus 2/3, which gives me 4/3, and a down, which is minus 1/3. 4/3 minus 1/3 gives me 3/3, or plus 1. As its charge. A proton is a baryon, so it has a baryon number of 1 because it has three different baryons in it. And that's a lie. Three different quarks in it, which each have a positive 1/3 baryon number, adding up to positive 1. And then it has a lepton number of 0 and a strangeness of 0 because it doesn't have any strange quarks, so we don't have to worry about it. Then my meson, the pion minus, has an up and a down quark. It's an anti-up though. So an anti-up has a charge of minus 2/3. So an anti-up is minus 2/3 E. And a down quark has a minus 2/3 or minus 1/3 E. So minus 1/3 and minus 2/3 together give us a negative charge. And then because they both have baryon numbers of 1/3, but one is it's not writing anymore. Oh, it's just really slow. Patience, apparently, is what we need. So anyways, the baryon number for my meson, this pion minus, is going to be negative 1/3 from the anti-up quark, and then positive 1/3 from the down quark, which adds up to 0. So we don't have a baryon number. And then my lepton number, because it's not a lepton, is 0. I don't have to worry about that. No strange quarks, 0. In fact, since there's no strange quarks in any of these and there are no leptons, I just know they're all 0. So that's pretty useful. Because again, if there's no leptons involved and no strange quarks involved, all of the strangeness and lepton numbers are 0. So then let's look at our charges over here. So our neutron has an up, a down, and a down. That's, as you can probably predict, going to add up to a charge of 0. And the pion neutral, or pion 0, you would imagine would also have a charge of 0, and since it has an up, which has a positive 2/3 charge, and an anti-up, which has a negative 2/3 charge, that also is going to add up to 0, which is pretty useful. Then when we consider our baryon numbers, a neutron has a positive 1 baryon number because, again, it's made of 3 quarks. which each have a baryon number of 1/3, adding up to 3/3 or 1 whole. And then we have our meson, which is the pion 0. And since it's a pion, it has a plus 1/3 baryon number and a minus 1/3 baryon number, adding up to 0. And this is taking a little while to load here, confusingly enough. But we can actually check and see if this reaction is possible. So to do that, I'm going to go through and I'm going to look at my 4 different conservation laws. Strangeness is all 0, lepton number is all 0, so we don't have to worry about them at all. But, come on, show up. Oh, it did show up. But we do need to look at our baryon numbers. So for our baryon numbers, we have a +1 on the reactant side. So I'm going to put a little line separating the two just so that I can see that they're separate. Oh my gosh, why is it lagging so much? Yeah, you can't tell that at all. That's okay. So I'm going to look at my reactants, which I'm going to compare the baryon numbers because, again, baryon number needs to be conserved. So in my reactants, we have a +1 and a 0. That equals total of +1. And then in my products, I have a +1 and a 0. And again, that equals a total of +1. So they're equal. That's good. That means so far it is possible. And then finally, I'm going to look at my charge. In my reactants, I have a +1 and a -1. +1 and -1 together equal 0. And 0 and 0 together equal 0. Hey! So that means, in fact, that the charge has been conserved. So this reaction is actually possible. Yay! It is possible. Go team. Okay, so let's look at this next reaction, and I'm going to switch out the recording if it keeps lagging so much. But so far, it's doing okay right now. So I've got a neutron, and again, I know a neutron is a baryon, and it's composed of an up quark, a down quark, and another down quark. Then I've got a proton, also a baryon. It has 2 up quarks and a down quark. And then an electron, that's a lepton. And its composition is just an electron, so that's not super exciting. And then we have an anti-electron neutrino. So that is also a lepton. It's an anti-lepton, technically. And it's made up of, again, an anti-neutrino, an anti-electron neutrino. Just to be clear, right here I have the sign. Here I have a whole line going over the top of this neutrino symbol, which I believe is the Greek letter nu. This means it's anti. This is just denoting the charge. I should be a little bit tidier. So again, I'm going to go through the exact same process I did last time, where I'm going to write down each of the 4 things: the charge, the baryon number, lepton number, and strangeness. Since there's absolutely no strange quarks, there's absolutely no strangeness to worry about. What a relief. Lepton number, I am going to go through, I'm going to say, well, actually, I have a lepton here, and all leptons have a lepton number of 1, and anti-leptons have a lepton number of -1. So that means my electron has a lepton number of 1, and my anti-electron neutrino has a lepton number of -1. Since I have a proton and a neutron, they are not leptons, so they have lepton numbers of 0. Okay, so then I'm going to look at the baryon numbers. I know that neutron is a baryon. That means that it has a lepton number, baryon number of +1. And the proton is also a baryon, so it has a baryon number of +1. The electron is not a baryon. The neutrino is not a baryon, so they have baryon numbers of 0. Finally, I'm going to consider the charge of each particle. And again, maybe you just remember that the charge of a neutron is, in fact, 0. But you can check on your IB packet and see that, aha, if it has an up quark, that's 2/3, and then 2 down quarks, that's -1/3, -1/3, that totals to 0. And so you can double check your math in terms of your charge. Similarly, my proton has a charge of +1. The electron, I know, has a charge of -1. And the neutrino has no charge whatsoever. It's an antineutrino, so it's like the opposite of zero, but because it's zero, the charge of the neutrino is zero. It is, in fact, zero, is its charge. Whew. Okay, so then we want to figure out, is this reaction possible? And so I'm going to, again, draw a little squiggly line separating my reactants from my products. So again, just like nuclear reactions, just like chemical reactions, I've got reactants and products. And each of these four things, the charge, the baryon number, so the charge, baryon number, lepton number, and strangeness all need to be conserved. So I'm going to go through the list starting at the bottom, because strangeness has nothing, so it is in fact conserved. So go strangeness, for sure conserved. Lepton number, we have 0 in the reactants, and then 0 plus 1 minus 1 in the products, which adds up to 0. So 0, that equals 0. Score, that is conserved. Go team. So lepton number is conserved. Baryon number, we have a plus 1 in the reactants, a plus 1 in the products. Plus 1 equals plus 1. It is, in fact, conserved. Win. Okay. Then we have charge, and again, 0 in the reactants, and then plus 1 minus 1, 0 adds up to, and also 0, and so it is conserved. And that means that this reaction is possible. It can happen that a neutron decays into a proton, an electron, and an antineutrino. And that is actually what happens when an element transmutates and decays into another element that has a higher proton number. This is what happens. One of the neutrons becomes a proton, emits that electron, which in nuclear physics we talked about as a beta particle, and the electron neutrino. So we're going to move on to number 3. I'm going to pause my recording and come back in a sec. Okay, so let's go ahead and try this third example problem. And I'm hoping that my computer won't be lagging quite so much. So here we have a proton and a pion minus. So proton, pion minus, decaying to become a kaon and a lambda particle. And I know these are mesons, but I'm going to have to double check on their composition. So I'm going to look in the worksheet that we already filled out. And if it wasn't listed in that worksheet, you could Google them and you could also figure out what their quark composition was. But a proton, I know that that is a baryon because it is made up of up, up, down, so 3 quarks. A pion is a meson. It's a pion minus, so that is the opposite of a pion positive. So that's an anti-up and a down quark. Then the kaon 0 is a down and a strange. So a down, and an anti-strange. Whew. And then it also has, it's a meson because it has 2 quarks. And then we also have our lambda particle. And the lambda particle is a baryon. Hey, I was wrong. I didn't know that. My bad. And it is made up of an up, a down, and a strange. What a weird baryon. You might call it strange. I know. It's okay. Okay, so then I'm going to go ahead and fill in my information I know about each of the particles. I'm going to do this in a slightly different order than I did before because it honestly doesn't matter what order you do it in. So I'm going to start by looking at the charge for each particle. So a proton has a charge of +1 because it has 2/3 plus 2/3 minus 1/3, which equals +1. The pion minus has an anti-up. Again, looking at my IB packet, anti-up has a charge that's opposite of the up quark because it's an anti-quark. So it has minus 2/3, and a down has minus 1/3. So that's a -1 charge, which we could have guessed by knowing it was a pion minus. But, good to know for sure. Kaon neutral has a down quark, which is minus 1/3 in charge, and then an anti-strange, which has positive 1/3, so its charge is 0. And the lambda baryon has an up, down, and a strange. I'm going to guess that its charge is 0 because, again, it's lambda 0, but let's just double check. So 2/3 for the up, minus 1/3 for the down, minus 1/3 the strange actually equals 0. And so if I look at charge, charge is conserved. So far, in terms of charge, it seems like this is in fact a reaction that could happen. But let's go on to baryon number. So for baryon number, we have a baryon that has a baryon number of +1, a meson which has a baryon number of 0, another meson which has a baryon number of 0, and then another baryon which has a baryon number of +1. Because again, none of these baryons are anti-quarks. I'm sorry, none of those quarks are anti-quarks, so it is a baryon that has a baryon number of +1. So again, if I look at conservation, I find it helpful to remember that there's a difference. Oh, that line is very large. Let's make it smaller. There's a difference between my reactants over here and my products over here. So if I look at baryon number, +1 and 0, and +1 and 0 means that baryon number is in fact conserved. Then we go on to look at lepton number. Well, since these are baryons and mesons, they have all lepton numbers of 0, which means definitely conserved. Strangeness, though, we do actually have to think about this time because we have some strange quarks over here in our products. Since we have no strange quarks in the reactants, they have strangeness numbers of 0, but our products have strangeness numbers of, let's see, anti-strange. All quarks have strangeness numbers of 0s, except the strange quark that has a strangeness number of -1. Ooh, okay, so the strange quark itself has a strangeness number of -1. So since this is a strange quark, not an anti-quark, it's a strange quark, it has a strangeness number of -1. Then the anti-strange quark has strangeness number of opposite of that, because again, it's an antiparticle. So that means it has a strangeness number of +1. Cool. So that means if I look at strangeness, +1 - 1 actually equals 0. 0 and 0 also equals 0. So strangeness is also conserved, and this reaction is indeed possible. So as you're going through these problems, I find it really helpful to make sure I recognize where are my reactants and where are my products. So I add a little dividing line between them just so that it's really easy and obvious for me to tell which values I'm comparing to determine my conservation laws and whether they're holding for that particular reaction. So good luck as you go through these. Give them your best shot, and then the next part is a quiz where you're actually going to be submitting your answers to these very problems.